Hello everyone. So we started our discussion on reaction dynamics in solution, and today we will be discussing about the effect of solvent in two important reactions. So again, this effect, we can say that this is actually a dynamic effect of solvents. Dynamic effect of solvent. So by dynamic effect, let us first give you an example. What do you mean by dynamic effect? Now, suppose I dissolve a molecule in a solvent, and usually it is assumed that when we excite electronically a molecule, suppose these are this is the electronic excitation that I am showing. Already these notations are familiar to you, S0 and S1. And suppose some molecule I am exciting, and what happens when you excite the molecule, since it's an electronic excitation, the electron cloud is now actually moved from one molecular orbital to another molecular orbital, as we have already talked about. So the electronic configuration changes, and you can have different electronic configuration, and out of that actually one is your singlet configuration in the excited state, which is the allowed transition. And then what you see here in that electronic state, there is a charge redistribution. Now usually in the ground state, for most of the molecules, the electrons are all paired up, and the charge redistribution or the dipole moment is very much very minimal, in the sense that the dipole moment will be close to zero. So we can say that the mu, the permanent dipole moment we are talking about here, the permanent dipole moment in the ground electronic state. So we can actually write it as mu d in the S1 state, S0 state is almost equal to 0. But what happens when it goes to the excited state, due to huge charge redistribution, we can actually have non-zero dipole moment in the excited state. Now what happens is, again, so this is related to what we discussed when we talked about electronic transition, the photochemistry part, and we said that there is a principle known as Franck-Condon Rule, and the essence of it is that the electronic transitions are so fast that the nuclei do not have enough time to reorganize themselves. It is not exactly Franck-Condon principle. This is an ansatz that we use in many cases, but the point here is that vibrational degrees of freedom are kind of frozen during the electronic transition. And what happens, all of a sudden, this molecule which we are exciting optically by shining visible or ultraviolet light, this actually creates an excited state permanent dipole moment, and then the solvent molecules around it try to reorient due to this new created dipole. Now we can actually draw a picture something like that. So suppose in the ground state I have a very small dipole moment. So usually the notation for the dipole moment is shown as an arrow, and we put a cross here. Some people actually do not write this cross here, so just to show you the positive and negative end. There are also other conventions. So we can actually show it just this is most likely the old convention of the dipole moment, and then this convention we can use just for our purpose. So from ground to excited state, so as you can see, the dipole moment was very small in the ground state, and in the excited state we have a huge dipole moment, and or we can actually show it as a very small charge redistribution. Suppose I have two ends in the molecule where I have small positive and negative charges separated by a small distance, and in the excited state I have a huge change in the dipole moment. So you can just use the similar notation. So I have delta minus and delta plus, and in the excited state the situation is something like this: delta plus and delta minus. Now I see that there is a big change in the excited state. There is a huge dipole created, and suppose momentarily when the dipole was created at time 0, which is very fast because it is an electronic transition, So then what happens, we can find the molecules. Let's say actually the molecules, we are doing this experiment in water. So momentarily we may found that suppose initially there was a water molecule which was in this position along the molecule, and then since we have a large dipole, this molecule has not changed its position. So the negative end, which is the oxygen end, so water molecules are also polar molecules. Now you see that this is a very much unfavorable orientation for this molecule, and due to that what the water molecule will try to do is that it will try to reorient itself so that this H end will actually face the negative end of this newly created dipole. Now if we do this experiment in polar solvents, so what happens is that the polar solvents will actually stabilize this excited electronic state much more than if we do it in a non-polar solvent. So in a non-polar solvent there will be little change, but in the polar solvent there will be huge change. And usually since the ground state dipole moment is almost zero, so the ground state stabilization in any solvent will be very negligible. So we see that we have actually drawn a few figures here. So I'll just write it once again. So this is the electronic states in the gas phase. This is what the excitation will be in the gas phase. This is in some, say, polar solvent, and this is in some non-polar solvent. So non-polar solvent, the excited state stabilization, the way I have shown it is little bit exaggerated, so it will be very similar. So what we see here is that in the polar solvent, usually the absorption line shapes are redshifted, because as you can see the energy gap between the two electronic state, ground state and the excited electronic state, is is actually going smaller. Whereas in the non-polar solvent it will be as if it is almost equivalent to the gas phase energy gap. So we can say that in the polar solvent what happens, the electronically excited state which had a large dipole orientation rearrange a large dipole due to charge redistribution, so that state actually gets stabilized. But this stabilization, the way we have drawn it, is not actually instantaneous, because nothing is instantaneous. The stabilization is happening due to the reorientation of the movement of the solvent, and that movement has some time scale. So this happens on the order of few tens of femtosecond. Those are the fastest time scales of solvation, to some few hundreds of nanoseconds or even more time scales. So it actually varies in a wide range of time scales. So this effect is known as solvation, which we are going to study right now. This is an example where the solvent molecules are dynamically controlling the energy levels of the molecules. Now, as often shown in many textbooks, that this picture which we have shown on the left hand side, what are the relative effects of, say, a polar solvent and a non-polar solvent in stabilizing an electronically excited state. This picture is a very static picture, and but the role of the solvent, you have to always remember, that is very dynamic. So that's why I call it as a dynamic effect of solvents. Another effect this effect is basically, as we said, is called polar solvation, and another effect of dynamic effect of solvents is in electron transfer. So both of which we will study. So first let us talk about the polar solvation dynamics, which you have already kind of schematically shown here. Now think about it, like we have an electronically excited state, and we showed that there is a potential for the electronically excited state, which actually will be a little bit shifted towards right, because of the reason that we said that the excited electronic state is always because of the fact that we know that in the electronically excited state, the electronic configuration is like HOMO -1 and LUMO +1. So in the sense that we have a change in the bond order actually decreases, and or the bond length increases, so the equilibrium bond position shifts. That we already discussed. Now this picture is very much intramolecular, in the sense all the energy levels we are showing is actually the energy levels which pertains to the molecule itself. However, in the presence of a solvent, what will happen, the electronic state itself will, as we showed earlier, will actually get stabilized with respect to time, as the solvents are reorganizing around this newly created dipole or newly created charge redistribution. So we can think that there is, apart from this intramolecular coordinate, there is also a solvation coordinate. Something like we can think that, okay, so there is an intramolecular coordinate, but overall there is also an coordinate which we can think about being the solvation coordinate. So the reaction coordinate here is the solvation coordinate. Now usually we do not actually show these both these pictures like small wells, harmonic potential well kind of picture or potential, where we are showing the intramolecular relaxation and the solvation. Now usually it is assumed that whenever you excite the molecule, the vibrational relaxation which happens within the molecule, which is the intramolecular process, that is very fast. So here the assumption we are making is that vibrational relaxation, which is intramolecular, of course, intramolecular vibrational relaxation is fast. And how fast it is? It actually completes within 1 picoseconds or few hundreds of femtosecond timescale. So again, this is an assumption. Now this assumption will be valid for polar solvents like, say, acetonitrile, but for polar solvents like water and methanol, we started with an example of water, but water is a very complicated solvent to study. And for those solvents like water and methanol, the solvation time scale actually is almost comparable to the fast time scale of vibrational relaxation. So you have to be very careful there, because there is a fast component of solvation which actually more or less equivalent to the fast vibrational relaxation time scale. But otherwise, it's a fairly good assumption to think that this intramolecular vibrational energy redistribution is fast compared to solvation. Now why we are making this assumption? Now think about it. So suppose we are exciting this molecule. Now you can think about detection, which is basically the fluorescence from the molecule which comes from the excited state. Now already we told that there is a rule. If you remember that we talked about a rule which is known as Kasha's rule, and which says that this vibrational relaxation is complete before actually emission takes place, and we assume that all the emission, the radiative emission, starts from the V equal to 0 state of the excited electronic state, which is the S1 state. And remember, it all started from the V equal to 0 state, from the ground state. That's a fairly good assumption. Now this Kasha's rule has a violation, because indeed what you see here is that as the vibrational relaxation happens, you also see emission from the excited state. So what you will see here, you will see an emission from all these states, and this emission, as you can see here, is that this fluorescence emission, initially for this emission, let us actually draw it once again just to make sure that the drawing is clear. So let us draw the energy level diagram of the molecule once again, and remember that all the excitation started from V equal to 0 in the ground electronic state, which we denoted as S0, and then it goes to all these levels, and that's the absorption. I'm not showing the absorption right now because we already discussed how the absorption spectrum looks like. Now we are saying that if there is any exception to Kasha's rule, how this fluorescence spectrum will look like. So suppose I have all these energy levels in all these levels actually corresponds to S1 state, and suppose we are having fluorescence originating from all these levels, say from V equal to 2, V equal to 1, as well as V equal to 0. Now as I have shown here, there will be of course a blue region of the fluorescence, where actually we see the fluorescence coming from the excited state, but those fluorescence will be of much weaker fluorescence, because in general Kasha's rule is violated, of course, because it says that it comes from the V equal to 0 state, but still predominantly the fluorescence actually originates from the V equal to 0 state in the excited electronic state. So in the fluorescence spectrum we will see a large contribution from this state, which actually is V equal to 0 state in the excited electronic state, along with some small contribution of fluorescence coming from all other states. So the interesting thing here is that all these fluorescence which are coming from different energy level has a time evolution, because we know that with respect to time the electronic states get stabilized, or the vibrational state gets stabilized, and we get a shift in the fluorescence. Now the way I have shown it is basically a vibrational effect, intramolecular effect. So there will be a shift in due to the intramolecular vibrational relaxation if we actually want to see or want to time resolve the fluorescence. And then we'll see also a shift in the fluorescence spectrum which is purely intramolecular. Now we are not considering that effect. What we are considering is actually solvation effect, in the sense that this change in the fluorescence due to the vibrational relaxation, that we are going to ignore, because the reason we are putting forward here is that this effect, this shift in the spectrum, fluorescence spectrum, is too fast to capture, and the contributions are also very little. So a major contribution is coming from the solvation effect, where actually there is of course a vibrational relaxation that will happen, and which will be much faster compared to after the excitation. But along with that, so this quickly actually comes from the V equal to 0 state, and then the entire molecule like electronic states are actually relaxing. So these are the vibrational energy levels. So all we are doing or we are saying in solvation is the emission from predominantly the V equal to 0 state over time, and now we are not talking about any intramolecular effect. So this is very important thing to know about, that we ignore the effect of intramolecular shift in the solvation. And in the similar argument we will see there will be a spectral evolution, the fluorescence spectrum will evolve with respect to time. So as you see, the fluorescence spectrum will actually shift with respect to time, and will have a predominant contribution of fluorescence coming from the V equal to 0 state at a later time, where the molecule has relaxed, and intermediate time scale we will also see the fluorescence coming from the V equal to 0 state, but at a much earlier time, and at a very early time we will see also the blue edge of the fluorescence. So thus we see that the fluorescence spectrum, which if we take a steady state fluorescence spectrum, it will be something like this, and we see that the small parts of the fluorescence actually comes at a very early time, the blue edge of the fluorescence, and the red edge actually comes at a very later time, and that is what we study or want to study in polar solvation. Suppose we also have a red edge fluorescence, something like that. So all we want to do is to time resolve this entire thing and detect how these fluorescence spectrum are evolving. And what I have not told so far is that you can actually construct something known as a correlation function, which is known as a solvation correlation function. We cannot talk about detail about the solvation correlation function. So the solvation correlation function says that if I take the spectrum at say infinite time. Now what is a infinite time spectrum? When actually the steady state has reached completely, the solvation is complete. At that time if I take the spectrum, so you will see that so this basically corresponds to the I mean after some assumption, the steady state spectrum So if I call the center of the spectrum, now I am writing nu here. Nu is the frequency unit, and the way I have drawn it is basically in the scale of lambda, in the sense that the wavelength actually increases, but in the other sense the nu, or more specifically the nu bar, the wave number actually decreases. So because if you see that the wave number is actually increased in the blue side, and with respect to time the wavelength increases, but the wave number or the frequencies are actually decreasing. So you see blue to red. Now if we tell that nu infinity is the infinite time spectrum, but again it's not exactly the spectrum, it is basically the central position of the spectrum. Now what we see here from the spectral shift, we can actually say, or we can actually define some parameter which will actually quantify how fast or how slow the solvation is. For example, suppose if I take acetonitrile and if I take some other solvent, say glycerol, how the solvation will take part, and then what you measure is basically what are the spectral position at different time. Now what is spectral position? Now spectral position, by that we mean that suppose at some time you construct a fluorescent spectrum and you find there is some spectrum at some particular time, and then what you do here is that you fit that spectrum with some known function. Usually you fit it with a log normal function, and then you call the center of your spectrum, let's say it was taken at time t prime, and then we call it as the spectrum at nu prime. So the center of the spectrum, we are calling it as a spectral position at that particular time. Now if you know that spectral position, then we can quantify something which is known as a solvation correlation function. So which is known as which we write it usually as C of t, which is identical to the spectral correlation function which we are writing right now under some assumption. I am not going into the details, and that basically tells you have to take the correlation function at any time is basically the spectral position at that time minus you have to take the spectral position at infinite time. Now, what is infinite time? Infinite time means actually when the solvation is over, the entire electronic state has fully relaxed, and that time spectrum, usually we assume it to be the steady state spectrum, and divided by it's not exactly the steady state spectrum. There is a So the spectral solvation correlation time is defined as the spectrum or the spectral position again at time t minus spectral position at infinite time, and this infinite time corresponds to the time when the molecule has fully relaxed, divided by, and we always want to normalize it. Now how do you normalize it? So usually this if we plot the solvation correlation time with respect to the time, then you will see an multi-exponential decay in the solvation correlation time, and if we want to normalize it, making that time 0 it is normalized, so you have to divide it by the corresponding 0 time definition. So it will be divided by time 0 and divided by minus time infinity. So as you can see that with respect to time, the nu of t that actually evolves, and all you need to know is nu of 0 and nu of infinity. Now nu of infinity you can actually get from your experiment. Nu of t you are measuring during the experiment. Now nu of 0 measurement, there are many like arguments how to measure the time 0 of solvation. Usually it is assumed that okay fine, you take the gas phase spectrum, but gas phase spectrum you cannot take, you take the molecular spectrum in non-polar solvent, because we already showed that in the non-polar solvent the shift will be almost similar as if gas phase, and in the non-polar solvent there is no solvation effect. So all the shift is coming from vibrational relaxation. So you account for only the vibration relaxation shift already, which is intramolecular, which you cannot remove, and then you see on top of that how much shift is happening. So this shift which we have marked here, that shift will be same as if I do this experiment in gas phase or in non-polar solvent, because that's a very intramolecular effect. And then we see how much it is shifting with respect to time, assuming that this vibrational shift happened much before that solvation occurred. And again, this will be true only for solvents like acetonitrile and many other solvents, but not for water or methanol, where actually the solvation might have a very fast component. Now this when you fit it to a multi-exponential and calculate the average time constant from that, so this time constant actually refers to the overall solvation time scale. Now this multi-exponential thing comes from corresponds to different motions of the solvent around it. For example, there could be very fast motion around the solvent of the solvent, so that suppose as I drew earlier, that initially there is a situation where the dipole has been created because the solute has been excited and the solvent around it did not have enough time to reorganize themselves, and they find that immediately after the excitation there is a huge unfavorable interaction. So what this water molecule will try to do is that this water molecule will try to abruptly move so that the hydrogen end, the delta positive end, points toward the delta negative end of this dipole, so that there is some stabilization of the excited electronic state of the solute, and that effect will be very fast. These are called inertial effect, and those time scale of solvation will be very fast. But then there will be overall slow motion where a water molecule actually moves and then reorients its hydrogen end to the negative end and vice versa. So those motions will be a translational diffusion motion type, and those will be diffusion control, and since diffusion has a longer time scale, those time scales will be reflected in the solvation correlation function, but as a longer time scale. So what I am saying here is that this entire curve, we can actually write it as like several time constant, a to the power minus a t by tau 1 plus a2 to the power minus t by tau 2, and suppose that tau 1 is smaller than tau 2 and so on. So in this case, this tau 1, tau 2 and tau 3 and all these time scales actually corresponds to particular solvent motions, like tau 1 may corresponds to the inertial motion, tau 2 may correspond to a longer motion, longer time scale motion, which are say diffusion mediated. So once we construct the solvation correlation function from the spectral shift, which is basically how the fluorescence emission itself is shifting over time, we can actually get an idea of this what are the solvation effects, and this correlation function basically quantifies the dynamics of solvation. Now one thing I want to point out here is that we have not talked here how you measure the fluorescence spectrum at different time, and secondly already we talked about this term which is known as Stokes shift, and you know that Stokes shift is basically the shift between the absorption spectrum and the emission spectrum that Gabriel Stokes observed, and usually it is used for both in the context of fluorescence Stokes shift as well as the Raman Stokes shift, but we are talking about fluorescence only here. So this Stokes shift itself, as we see, evolves with time, because there was an absorption which we did not show here prior to the emission. There are absorption to all these states here, and then we had we can actually draw it here. So when the absorption happens, so due to absorption there is an absorption spectrum, and due to emission there is a fluorescence spectrum, and this is the Stokes shift. But what we are saying right now is that the Stokes shift itself evolves with time, because there is an absorption and you see that there is a shift due to early time fluorescence, then eventually there will be a shift due to the late time fluorescence. So we are actually measuring the dynamic Stokes shift here, or sometimes it is known as time resolved fluorescence Stokes shift measurements, because it's not a Raman Stokes shift. So fluorescent Stokes shift experiment, so it's called TRFSS, and all these I mean the terms are self-explanatory, and or sometimes it is known as the dynamic Stokes shift, as opposed to the static Stokes shift, where you basically talk about the Stokes shift, which is just between the overall absorption spectrum and the steady state fluorescence spectrum. So your steady state fluorescence spectrum actually is a time average spectrum of all these fluorescence spectrum that come at that originate at different time. So we'll conclude our discussion on polar solvation dynamics here, and now we'll switch to the second topic, which is the electron transfer reactions, and there also we'll see the solvent actually dynamically how it influences the rates of electron transfer that was explained by Rudy Marcus.